Morning. Can you hear me? Okay. Thank you. So today I have a colloquium in the afternoon. So I will give only maybe 1 or 2 hours, and then Pablo will take control and will discuss the second lab. So today I want to talk about generalization of what we did yesterday, namely the energy estimate and the proof. How much can we extend the proof of stability, uniqueness, existing uniqueness and stability. So I'm going to talk about strongly hyperbolic systems. So before we were talking about symmetric hyperbolic. That is, we look for some, we have a system, I think we call A alpha beta, grad U beta equals to J of alpha, and we look for a matrix, positive metric, gamma alpha, such that when you do this, it was symmetric. With respect to the two indices that are free, this and this one. Okay. So, for instance, in 4 dimensions, 3 space 1 time dimensions, what we have here are 4 matrices, and we require an H that makes the 4 matrices symmetric. And then we require also that H gamma alpha A alpha beta times some NA, this be positive, right? So that was the condition. So, and due to this we got energy estimates. Which says, the energy estimate is something that says that the energy at some time, or better, the derivative of the energy at some times is less or equal to some function of the energy, with this function on 0 being 0. So that tells us that this E of t is bounded by the solution of E of t, where E of t is the solution of dy dt equals now to f of y, and with E of 0 equals to E of 0. Okay? So we have that this function is bounded. And that means at the end of the day that this what it says basically, since this is initial, depends only on the initial data and the solution only depends on the initial data, that the energy is bounded by the initial data. No matter what initial data you take, you have a bound, okay? You change the initial data, you change the bound, but you have a bound always. So this is what we want to have. So we know that since this function is continuous, we know that the energy is a continuous function of the initial data. So and this is important because it tells us that we have a stability, okay? And we saw yesterday that also this energy conservation, at least in the linear case, gets to us to proof of uniqueness and existence of solutions. So this is the real important thing. So now I want to see, is this condition, symmetric hyperbolicity, the most general one, or are there more general conditions that give me stability? This is the question. To answer that question, then we can go to a simple problem and solve it, and we'll see there what happens. We did some part of that before, so it will not be too difficult. So we go to let's say in one dimension, we go to a circle. I don't want to use a red. We go to a circle, and we have so the space is a circle, so the evolution of the space is a cylinder. This is time here. And so we are going to solve some problem here, and we say the u dt equals to, so we just write in 1 plus 3 dimensions, di of alpha beta at I of u beta plus j of alpha. Okay, some equation like this, and we will think of, for the moment, constant coefficient. And this is, we'll just take 0 for the moment, okay? Or we can take, if you want, these j's to be some alpha beta, j beta, u beta, sorry. Where this is constant. So it's simple system. So if these are constant, we can use Fourier series. So we span in Fourier series. So we write the u alpha as a sum over the Fourier basis. How do we call it? U hat alpha n e to the n. This is the base in x. This is a function of x. This is a function of t. And where u alpha n has two indices now, is u alpha with the base. I think I have to put it the other way around. E to the n, and here u alpha. This is a hat, huh? These are Fourier coefficients then, and we have this, and then the equation becomes, for the coefficients, right, becomes just an ordinary differential equation. I'll put the n's downstairs so that doesn't bother in the notation. And this is, I have this matrix here, and because I'm taking derivative, I get a k n, which is this. We're assuming that the derivative of the base element is ik an. Okay. Sorry, this is x. And here we have u hat and alpha. So we get an equation for each coefficient which has this form. Okay. And so this is the wave vector, right? This case, in this case, if say if we are in the circle of units, or well, in general, this is 2 pi n over the length. Okay. Yes. So you get this equation, and we know the solution of this equation. The solution is the exponential map. I see I'm mixing something here. I was doing in one dimension, but let me do in more than one dimension, because in one dimension everything is quite trivial. Let me do it in more dimensions. So instead of a circle, we have a torus, okay? We have a torus. T dimension is, base dimension is n. So this is the same here. The only thing is that these are vectors, right? These are n, etc., which I'm going to call still kn, which has just one index. So I will put here the index of the k. So the solution for that is let me call a times k. Okay, a is a matrix, and you have this I. There is an I here, and I have a t here, and I have the values of these coefficients at 0. Okay, this is a solution. So what I make a claim now. The system is well posed. In L2, if only if the matrix norm of this thing is bounded. So this thing can be unbounded in two ways, because t goes to infinity and because k goes to infinity, right? So we can think of, in fact, the important thing is how the product goes, but the thing is you can be at finite time, any finite time, but the wave number, these numbers goes to infinity. So you want to keep this bounded for all these numbers, okay? If we were doing this in Rn instead of Tn, so using Fourier transform, then this k will be just a vector, any vector in Rn, so we have to have this bounded for all the values of k, even those that go to infinity. So let me tell you why this is so. Suppose I have these fields and I have some scalar product, say, so you take the normal 2 of u. Let's think about the scalar product as just in this base, in some base. So it's this by the Plancherel identity is just this thing in the norm L2. So here the norm we are taking is just the first component square, the second square, the clear norm in these components. Okay. So for each one of them we have the Plancherel identity, so we can sum them and we have that the norm L2 of u in L2 is equal to the norm of u in this small L2 or the big L2 if we are in Rn. And this is the norm of e to the I a kt times u at 0. So if this is bounded by some constant, this is a sum over all the n's, right? So if this is bounded by a constant, universal constant, that this doesn't depend on the sum, this is less or equal to this constant times the norm of u naught in L2, square here. And this using Plancherel again is less or equal to c times the norm of u at 0, the initial data. So if we have this, then we can show that the system is stable, right? This is stability, because it tells me for linear system that the thing we saw that the solution at some time is bounded by initial data, okay? So this is the end result of this calculation. So we have the if, right? If this is bounded, then the system is well posed. The only if is a bit more complicated. It's a bit, not much. You can find a sequence now of initial data. Let me put the index, the sequence in this Q. You can find a sequence of initial data such that, if this is false, such that when you go to infinity with the sequence, the norm of the initial data for all of them, so the norm of this is finite, is bounded, while for any time t larger than 0, this thing goes to infinity. Okay? You can build it. And why so is that? Well, because if this is not bounded, you start looking, you can pick case where this is bigger, bigger, and bigger. So you take the sequence with these conditions, just taking in the sequence the eigenvalues of these that go back, the eigenvectors, and then you can build this sequence, okay? So what we need is this condition. This condition provides stability. And here is important, I'm just taking the L2. You can have you can violate this condition and still have stability for some problems, but instead of using this norm, the L2 norm, you have to use another norm, okay? So there are different concepts of stability depending on the norm, and the conditions you need are different. But this is very important, this condition, because it allows, for instance, to have here things that go arbitrary b's here. They don't bother, because if you put a b here, right, this will change in some other term here that will go like plus b, okay, without the k and times t. And this term, for finite times, you can bound with the maximum value of t and the maximum value of this norm. So this is not problem. The real problem is when you allow k go to infinity. So the real problem of stability is when you allow higher and higher frequencies, when k goes to infinity. Because that means if you have a solution, a nice solution, and put some noise on it, you want that the solution of that will go with a small noise. And if this thing is not stable, what happens is this goes to something with a lot of noise. Okay, so the solution move to this, but the solution with the noise move to this. Okay, so you get something very small going very bad. This is, we did these examples already. So this is the condition. So now it's a question on matrices, right? When is this thing bounded? When is this e to the k I in this case? Let me pull k is bounded. The t we get take t equal to 1. When is this bounded? And there are 3 conditions, actually 4 conditions that are equivalent to this. So we have equivalence. And these conditions are the following. 1, there exists h of k, alpha beta. I was using the, let me use the same notation. H alpha beta of k, such that this thing was symmetric. It was symmetric. And h such that this is symmetric, and h alpha beta is symmetric also. And positive. Okay? So if we find this h, which might depend on k, if h doesn't depend on k, we are in the symmetric hyperbolic case. Okay? Because if h doesn't depend on k, what we are saying is all these matrices taking k unit vectors in different directions, all these matrices were symmetric. But here we allow that H depends on K. Okay? Is this different from symmetric hyperbolic? Yes. There are systems which are strongly hyperbolic. This is a condition of a strong hyperbolicity, what we are discussing now, which are not symmetric. Okay? So this is a bigger set. So you have here the strong hyperbolic system, and here you have the symmetric. So this is the first thing is that there exists an H, and then you will use this H alpha beta to make the norm for the hat components, okay? In the Fourier space. They depend on K here. You will use this norm to make the energy in the Fourier space, and then you will go back to the real space. So you say, okay, but you are doing constant coefficients. Okay, what happens if you have an equation which is not constant coefficients or not, or is not even nonlinear? And then the condition holds, still it holds and give you existence, but the proof of these things is very technically very complicated. You have to use something that's called pseudo-differential. How do you write it? The other way around. Calculus. Okay. So what you do in general is to define, for instance, for this, given this, you define some operator, H, that acts on functions, and the action is you, well, in this case, which is Fourier, you say this action is, you go to Fourier space, look at the components. So here you have a sum where the components. Go to Fourier space, apply this operator here. So this was for things with an index alpha here. Apply the beta alpha of K to U hat of alpha, where this is the Fourier transform of this, and then apply to the base and do the sum, right? So you apply this, and if these things were dependent on xi, so that this also have an x here, and this depends on x, so this also depends on x, then you have an x here, and you define these things with the x here, and you work out. This thing is quite complicated. It's all a whole technology on this, but doesn't matter to us really. So the first things then, the first condition that is of this equivalence is that you have this H, and with this H, doing things like that, you get an energy estimate. Right, the energy estimate will be U beta H U alpha, where this H is now an operator. It's not a matrix of that depends on X. It's some operator. Okay. So you still get the energy estimate, but through these operators. The second condition is that A is A of k, that there exist, let me exist S of k, and of course it since depends on x is S of k and x, such that the norm of this thing and the norm of the derivative, the matrix norm, and are uniformly bounded, of the inverse are uniformly bounded, such that S of k, A, I, k, I, S minus 1, S of k is diagonal. I'm taking the I, so it's with the real entries. Okay. So as we saw, and this is why, because we saw that if you have a matrix with a Jordan block, say you have a metric A, and here for some k you have a Jordan block, so for instance a 1, 1 and 1, 0, then this, when you take the exponential of this matrix, you will get here some e to the lambda, which is the, let's put lambda here and lambda here, e to the I lambda, in this case because we are putting an I here, t, and then you get a polynomial in lambda, right? And lambda depends on k, so when k goes to infinity, this polynomial will go to infinity, and so these things are not bounded. So we knew from the beginning that we have to obtain this diagonal condition. The third one is a condition that says that if you look at the inverse of S times the identity minus A inverse, sorry, this inverse, then this is less or equal to some constant times the imaginary part of S. So now we take some S which has some imaginary part and look at all the this is called a pencil, right? You move with this I along the A's. And what happens is when you cross an eigenvalue, right, with this, you apply this to a vector. And if this vector is an eigenvalue, here you will get S minus lambda ui, where this is a eigenvalue and this is a so this, when you cross this, if S is real and these are reals, you get a 0, and so the inverse doesn't exist. So what you are saying here is, okay, I'll take some S with imaginary part, and when I do the calculation, I find that this is not satisfied because the eigenvalues are real, right? But I approach, if I try to approach the reals in S, I will get a pole that goes like 1 over S, okay? Let me give you an example. If you take this system, k being 0 or 1, then if we do this, we get s minus lambda 1, s minus lambda 2, k 0, minus k 0. This is this metric. The inverse of that metric is let me check, I think it's 1 over s minus lambda 1, 1 over s minus lambda 2, and here is k over s minus lambda 1, s minus lambda 2. I think it's this one, because if I do this by this, I get 1. If I do this by this, I get k over s minus yes. And if I do this with this, I get 1. If I do this with this, I get 0. Okay, yeah. It's this one. So this is the inverse. So this is, let's use some other color. This in here is this. And you see, if lambda 1 is equal to lambda 2, I have a pole here in this component that goes like s minus lambda square, right? If these are equal, so if they are different, the two poles are like this. They go. So I take now s to be lambda 1 or lambda 2 minus I epsilon, right? In this, when lambda 1, so here I will get a 1 over epsilon, here I will get nothing important, it's finite, and here I get a 1 over epsilon, if lambda 1 is different from lambda 2. If both are equal, lambda 1 equal to lambda 2, then here I get a 1 over epsilon, here I get a 1 over epsilon, but here again 1 over epsilon squared. So this fails, okay? So that's why it works. So it's ruling out this, huh? And so if you take out all these Jordan blocks, you get that the system is diagonal, which is condition 2. So we can go this way for condition 2. And condition, once you have the system is diagonal, you can build this H, because you take the eigenvalues, eigenvectors, and with the eigenvectors you build the H. Okay, so this is how it works. And then there is another condition, which is, this is a condition that was done by a student of mine, Fernando Avalos, and these conditions, the first condition is the singular value, the singular values of a singular value decomposition go to 0 at most linearly. So what you do is, what is a singular value decomposition? Suppose you have a metric, not necessarily square, any metrics. Then you can build with this metric the adjoint, or and this, and you can build. So this will be, suppose the metric is like this. So the adjoint will be a metric like this, and you will get this with this is one component, this with this is one component. So this will have a, it will be a metric which is smaller, right? Because we are doing, so that will create a metric which is of this, of the entry of this, of the dimension of the entry of the metric. And you can do the other way around. You can do A times A star, and this is going to be a multiplication like this. So you multiply this here by this here by this, and so on, and you get a bigger matrix, right? That has a dimension of the image. And now what you do is to compute the eigenvalues of this thing and the and eigenvalues of that, and so now you come with these eigenvalues, you build some matrices W and B, which are different because this is a small metric and this is a big metric, so that with the eigenvalues you build these two metrics, and so the resulting thing here is that this metric has a form sigma 1, sigma n, so a square matrix and then zeros here. So the kernel gets out and you get these sigma 1s and these sigma 1s, sigma I the square root of the lambda i's, which are the eigenvalues of this metric, u equal to lambda I ui, right? So this is a singular value decomposition. And what you want to see is whether this is diagonal, but this is a diagonalization with matrices that are different, right? It's not diagonalization like s to the minus 1 s, which will be in the square case. It's with this matrix. And now what you have to check is whether these eigenvectors, eigenvalues, go, when they go through 0, you do this for this matrix, the pencil, again. And you check whether when you go near the eigenvalues, you will get a decay, a 0 that goes linear or higher order. If the zeros go linear, that means that the system is diagonalizable, and if the zeros are not, it means that it's not, right? And the proof of that goes from here, you can go to here. Oop. Sometimes get crazy. I think I have to go out. Okay. So you go from here to here. And this is a good condition because you can apply it to systems which are not square. When you have constraints, you have systems which are not squares but are like this. A system with constraints is like a system like this. So we are going to use this later on at the end of the course. to discuss more in details system with constraints. So this is strongly hyperbolic systems are systems which are stable, and you can characterize which any of these conditions. Okay, they satisfy all of them. This singular value decomposition is very important. It's used in all kind of technical things, because what it does is when you split this, you get here the eigenvalues. And for many cases, what happens is that there are eigenvalues that are very big, and then there are eigenvalues that are very small. But in many cases, what is important are the big ones. So you can reduce the metric throwing away all the smaller ones. So you do the singular decomposition, compute these things, throw away the small ones, or just compute the big ones, and then rewrite the A but without this. So from one matrix A, you go to some other metric, hat, where you have thrown away many of these things. And this is used for passing information, fast information for image processing, etc. It's a very good technique in practice. So it's good to know something about it. I think let me show you something. I am preparing my talk for this afternoon. I have a picture here of that. Yeah, this one. So you take this image and you think of it as a matrix with the blacks are 0 and the whites are 1. And then you do the singular value decomposition and start taking different eigenvalues. This is a list of eigenvalues. And then you can cut. For instance, if you cut to the first one, you get this very blurry image. But after these 5 eigenvalues, you get a very, very good image. So you see this is not the same as this. For instance, this one is not in the original one, but it's very close. And here there is one extra. There is one that is also extra here. But it's a quite good representation of the original picture. So that's the way you use it. So let's take 15 minutes. We continue at this. Already covered all the things I want to say today about the strong hyperbolic system. We continue at 15, okay? No, 10, sorry. Questions about this? So, no questions? Okay, we take the break then.